Okay, so this is where we stopped the last time. We expressed the water equation in terms of P naught. And now we're just rewriting equation 3, the oil equation, in terms of SW. Because, like I said, SO is just 1 minus SW. So nothing special. So these are the two equations, and now they are clearly in terms of oil pressure and water saturation. So it's two equations in two unknowns. Next thing we do is to simplify the notation on the right hand side by introducing the inverse of formation volume factor. So small b is inverse of formation volume factor. So this is for oil, this is for water. So that the right hand side can be written in this form, which is more succinct, right? So phi SW small bw in place of phi SW divided by BW. Same for the oil. And technically, we can write it again in terms of SO. And whenever we're done with the discretization, we will use this 1 minus SW in place of SO. So this is what it is basically on the right hand side, which is precisely the same as. All right. So nothing fancy here. And now I'm going to take out all of this just to minimize the liter. And so we will start out by discretizing the right hand side. And I explained, this is the question you guys worked on, question number 2 in your midterm. How do you discretize the right hand side? Backward first order difference, right? So first order backward difference. And then we start out with the oil discretization. Phi B naught S naught will be 1 over delta T, right? Then current time step, previous time step, and that's what this is. So phi B naught as current time step minus phi B naught at previous time step divided by the time step size, which is delta T. And the next couple of processes, again, you can pause the video at any time and read through the derivations, watch the video again. But this is the rigorous process to discretize the multiphase flow equation. So we subtract and add this term from the right hand side. So we are going to have this term, right? Minus this, which is here, plus the same term, this guy, minus this other term, which is this. And now you can collect this term outside the parentheses, right? So that is this. And then you have S naught at n plus 1 minus S naught at n. That's what this is. And do the same thing on this side. Combine these two equations. Take S naught out. That's what is common. And this is what is left. Now, we work on this second term. We add and subtract phi at n, B naught at n plus 1, so that we can obtain this. So when you collect the like terms, it will be this term right here, minus what we're adding and subtracting, minus this. So what is common? B naught at n plus 1 is common, right? Which is this. So I actually showed the step here. So this term is this term. We subtract this and add it, and then subtract this. And when you factorize these two, you get this term. Factorize these two, you get this term. This one is identically same as this. we can take the delta t into the parentheses, right? So this is the term that is changing. You can divide that by the delta t. This other term is constant with respect to delta t. Same with all these except the terms with the minuses. So the terms that get divided by delta t are the ones I'm highlighting with the red. And that's what you see here. So this gets divided by delta t, this gets divided by delta t, this gets divided by delta t. Now we can work on these two terms. So this is basically defy the t, right? This is defy the t. This is dB dt. And as you can see, they are both functions of pressure. And this is a function of pressure through compressibility. So what is defy dt? You can use chain rule as shown here. This is chain rule. And we want to use a shortcut for defy the p as phi prime, which is technically this. It's phi at n plus 1 minus phi at n divided by p at n plus 1 minus p at n, right? And you can easily evaluate this in your simulator. For slightly compressible fluids, we will typically work with rock compressibility when the system is slightly compressible. And in that case, we use the definition for rock compressibility, which is actually given here. So 1 over phi defy dp. But this phi is a reference porosity, which doesn't change, right? And that's what is shown here. Because you can multiply both sides by phi naught, and this becomes phi naught CR. So this is a reference phi, the PDT. Can do something similar for B. So to differentiate the B, to differentiate B with respect to time, use chain rule again, get this, and you can replace this by B naught prime for brevity, right? And then, of course, I already talked about this, right? Those are the saturation constraints. Now we proceed and then substitute these definitions for the BDT and defy the T into the equation shown right here. So this term does not change. This is where we bring in defy the T, which we derive right here. So it's now a function of pressure. Same deal with this term, is now a function of pressure. And that's why we do those manipulations. That's why we add and subtract first this and then this. That's all that got us here. Good. So the final step here is just to rewrite it in this form where we have evaluated 1 minus SW. So what we did was to replace S naught with 1 minus SW. And then the negative sign shows up in front here because this will become SWN minus SW at n plus 1. And we still want to maintain it in this form, so we put the minus out here. And the other term remains the same. We just collected these two functions of the PDT. And what we like to do when we implement reservoir simulators is to call this term D1, D22, and call this term D21. And you will see how that fits naturally into a matrix formulation. And at this point, I'd like to stop this video, then continue in another video.